Good afternoon, everyone. My name is Davide Sulcanese, and I am a PhD student at the University of Annunzio in Pescara, Italy. And this afternoon, I'm going to talk about Venus volcanism, specifically about the insights into volcanic activity and surface evolution. So, let's begin with an overview of what I will be covering in this presentation. First, I will introduce Venus morphology, volcanic activity, and resurfacing history to provide context for the rest of the discussion. Next, I will review previous evidence of recent and ongoing volcanic activity on Venus, highlighting the past findings. And then I will present the results of my latest research paper about new evidence of ongoing volcanic activity on Venus derived from our analysis of the Magellan data. We will delve into the results, explore all the alternative interpretations of these observations, and discuss the hypothesis of new lava flow. So, let's delve into this first part about Venus morphology, volcanic activity, and resurfacing history. A key concept in the study of Venus is that it's not possible to observe its surface directly from space using visible light imaging, as we typically do for Earth, Mercury, and Mars, for example. And this is because Venus is enveloped in a thick layer of clouds, primarily composed of sulfuric acid, which reflects and scatters nearly all the visible light. Consequently, to investigate Venus' surface, we must use longer wavelengths, such as the microwaves, which can penetrate the dense atmosphere and reach the surface. Therefore, all space missions aiming to observe the surface of Venus in high detail have been equipped with the synthetic aperture radar. I put here all the missions until now that were equipped with this instrument, which were the Venera 15 and 16 of the Soviet Union, and the most important one until now, the Magellan of the NASA, launched in 1989. So these missions were equipped with a synthetic aperture radar, which use indeed the microwaves to map the planet's surface morphology and topography, and especially the geological features. These are just a couple of images acquired by the Magellan. So, these images reveal for the first time a world full of volcanic features, some of which were already present, were already been observed on Earth, such as large shield volcanoes. This is an example of, this is Sif Mons, one of the main volcanoes on Venus. Small shield volcanoes, which are volcanoes with a diameter of 5 kilometers or less, and huge lava flows and volcanic plains, but also morphologies that are present only on Venus, such as the coronae, the novae, and the arachnoids. The coronae are large circular to ovoidal-shaped structures and often have hundreds to thousands of kilometers in diameter, and are characterized by these concentric and radial fracture patterns. And they are thought to form through upwelling and deformation of the lithosphere, possibly driven by mantle plumes or diapirs beneath the surface. Then the novae are these starbust-like features with a central uplift and radiating fractures around. And they often represent localized magmatic intrusion that cause the crust to fracture radially. And then the arachnoids, which are considered a subcategory of the coronae, but are smaller and consist of concentric rings with a web of radial fractures, and that's why they're called arachnoid. And also the formation mechanism is related to process similar to those that form the corona. So also in this case, diapiric activity or plume activity, but of course, at a smaller scale. So these volcanic-related features cover almost the entire surface of Venus. And therefore, we can state that volcanism on Venus is the main morphogenetic agent responsible for reshaping its surface. What is known is that the surface of Venus is, geologically speaking, young, with an estimated age between approximately 0.50 up to 1 billion years. However, there are still uncertainties regarding the mechanism of this resurfacing throughout the geological history of Venus. The randomic distribution of impact craters across the surface, which provides the basis for age estimates, is compatible with several different resurfacing scenarios. In the first one, called catastrophic resurfacing scenario, the surface of Venus was completely wiped out by a sudden event, such as global volcanism or a crustal overturn, followed by a period of little to no geological activity. This catastrophic event may have occurred only once in the geological history of Venus, as proposed in the singular event scenario, or multiple cycles of abrupt events followed by periods of little to no geological activity could have taken place, as suggested in the recurring event scenario. Then, in contrast to this catastrophic resurfacing scenario, another model has been proposed, known as equilibrium resurfacing scenario. In this other case, the surface of Venus is continuously reshaped by volcanic activity over time and across its entire surface. Lastly, the regional equilibrium resurfacing scenario falls somewhere between the catastrophic resurfacing and the equilibrium resurfacing scenario. In this case, the resurfacing occurs with spatial and temporal variability, meaning that only certain portions of Venus surface are active at any given time, and these areas change over time. So, as you can see, there are still significant uncertainties regarding the evolution of volcanic activity throughout Venus' geological history. And therefore, understanding whether Venus is still volcanically active today, and especially to what extent, would be extremely valuable. So, there is much indirect evidence suggesting that Venus has experienced recent geological activity and perhaps is still active today. Here, I will open a brief parenthesis about the concept of recent volcanic activity, because in geology, a volcano is considered active if it has been active during the Holocene, meaning within the last 11,650 years. So if you heard someone said, okay, this lava flow is recent, it could be also thousands of years old. Instead, when we talk about ongoing volcanic activity, it means that it's active today. So one of these indirect evidence is the detection of emissivity anomalies in some of the main volcanic edifices. I put this example from the paper of Smecker of 2010, in which they spotted some high emissivity anomalies on the top of some volcanic edifices, and they interpreted these emissivity anomalies with unweathered lava flows. So in this case, they infer a geologically young activity. Then also variations in the volcanic-related gases, such as sulfur dioxide and the phosphine in the atmosphere on Venus, has been analyzed to infer, in this case, the ongoing volcanic activity on Venus. Then, in 2023, a reanalysis of Magellan radar images provided the first direct evidence of ongoing volcanic activity on Venus. Specifically, by analyzing images of the same area taken at different times, Eric Densley detected and measured a deformation of a volcanic vent on the northern flank of Mat Mons, which is another volcano located in Atlareggio. And they interpreted this deformation as ongoing volcanic activity. So, similarly to this recent work of Eric Densley, the goal of our study was to search for possible changes across the surface of Venus by comparing images of the same areas taken at different times, performing what is known as a radar change detection analysis. So, the Magellan mission conducted 3 different observational cycles, each following the other at 9 months intervals, starting from September 1990 up to September 1992. Now you're looking at the first observational cycles, which is a left look cycle, meaning that while the spacecraft orbited from north to south, the radar pointed to the east. And this cycle alone, as you can see, covers the 83% of the surface of Venus, almost the entire surface of Venus. Then the second cycle, from mid-May 1991 up to mid-January 1992, was dedicated to filling the gaps of the first cycle. And indeed, with this second cycle, the global coverage rise to the 96%. The second cycle is a right look cycle, meaning that the radar pointed to the west. And then the last observational cycle, the third one, which is, like the first one, a left look cycle, even if in this case the incidence angle are lower than the first one. Later on, I will explain you what is the incidence angle and why it is so important. With this third observational cycle, the global coverage rises to the 98%. So what we did was to compare the images that looked at the same area, both in the first and in the third observational cycles at least. And that is because the first and the third share the same look geometry. So it's easier to compare the images of the first and the third observational cycle. So an important part of our work was to properly process the images. And that is because, as you can see, if we take a look and if we compare 2 cycles not processed, the images were not properly aligned and are quite noisy. So what we did was to perform a co-registration in order to have a better alignment. Then we converted the pixels from digital number to backscatter, and then we applied the speckle filter to better clean the images, which is called, in this case, we use a Lee filter, in order to have the images ready for our change detection analysis. So our analysis revealed two different regions on Venus in which the backscatter significantly changed between two or three different observations. The first region is located on the western flank of Sif Mons, the volcano that I showed you before. In this case, we have available only the first and the third observation cycles. And after performing our analysis, we noticed two different, let me put the laser pointer, two different features in which the backscatter significantly increased in the cycle 3 with respect to the cycle 1. And if you take a look at these green dashed lines, which are the surface tracts of the backscatter cross-sections in panel E and F, there are some regions pointed by the red arrows in which it is evident how the backscatter increased in the cycle 3 with respect to the cycle 1. Then the second region is located in the western portion of Niobe Planitia, which is one of the main planitie in Venus. And in this case, we have all the three observational cycles. And also here, in the third observation cycles, some bright features appeared. And also in this case, if you take a look at the backscatter cross-sections, it is evident how there are some peaks in the third observational cycle not present in the first and in the second one. So after observing and analyzing these features, we began to consider what could be the possible causes behind bright features we observed. So, as a first hypothesis, we consider that the feature we observe could be due to a difference in incidence angle. The incidence angle is the angle between the radar look and the normal to the surface. And since these different cycles have different incidence angle, these features that we observe could be due to such difference. So what we did was to analyze, thanks to the Muleman model and the Agforce model, this behavior of the backscatter. These models broadly expressed this relationship between the incidence angle and the radar backscatter. However, in both the models, even if we put our incidence angles in Sif Mons and Niobe Planitia, we cannot reproduce the difference that we observed. So for this reason, we excluded this hypothesis of the difference in incidence angle. Then we also considered the atmospheric effects. And that is because on Earth, the rain droplet can scatter the radar signal and produce this kind of effect, such as the attenuation or this white veil. And on Venus, there is some kind of droplets, but it's of sulfuric acid. But the size of these droplets, which is in the order of the micrometers, is too short to scatter the S-band signal of the Magellan, which wavelength is of 12.6 centimeters. So also in this case, we consider very unlikely this hypothesis. Then we also do not consider geometrical effect, common geometrical effect of the radar, such as the layover, the forest shortening, and the shadowing, or the azimuth ambiguities, which is this repetition of the signal across the azimuth, because the features that we observed have different lengths. There is not a geometrical repetition, no specular reflection. And most important, as I will show you later, some of these features seem to interact with the surface obstacles. And so, for this reason, we think that the features we observe are actual alterations in the geophysical characteristics of the terrain, such as variation in topography, a variation in roughness, or a variation in dialectic properties. So, in these 4 points, in this 4th point, there are also other hypotheses. So, we have also considered the hypothesis that the structure we observe could be landslide deposits. On the left, you can see an example of 2 landslides that occurred along the northern flank of a shield volcano on Venus. And in this case, the source of the landslide is the volcano, and is clearly visible, as well as the 2 slip surfaces, which are the surfaces over which the landslides traveled, and the landslide deposits, which appeared as patches with heterogeneous backscatter. On the right, you can see some bright features that we have identified in Niobe Planitia. And in this case, the origin of some of these bright features can be traced back to small shield volcanoes present in the study area, with a diameter of a few kilometers. However, given that the expected height of these shield volcanoes is only a few hundred meters, and the regional slope of the study area is essentially negligible, we would not expect any potential landslide deposits to extend for more than a few kilometers, as illustrated in this diagram by Melin et al., in which the length of the putative landslide deposits is expressed as in function of the height of the escarpment. Nevertheless, the structure that we observe extends for tens of kilometers, making this hypothesis of landslide deposits unlikely. Then we also consider the hypothesis that the feature we observe could be dunes or microdunes. This is very interesting because given the asymmetric nature of the dunes, these features could be visible or not, depending on the radar look geometry. This is an example of the Stowaway crater region, in which these features are visible in the cycle 3, but are not visible in cycle 1. This is very similar to what we observe. However, in this case, we have to do some considerations. First of all, the surface winds on Venus are very weak. And therefore, all the dunes and microdunes deposits on Venus, which are very few, are located nearby their source of sediments. Their source of sediments. In this case of Solway crater, the crater itself. However, in both Niobe Planitia and Sif Mons, we do not observe any potential source of sediments that can produce dunes. Furthermore, if we consider Sif Mons, it is located at 2,600 meters of height, and at that height, the surface winds are even weaker, and so it's very unlikely that the dunes can form in that condition. And as regards Niobe Planitia, we further investigated this hypothesis of the dunes. So this is the first look, the cycle 1. This is the cycle 2, quindi, so right look with the incidence angle of 25 degrees. And then the third cycle, also in this case, 25 degrees, but left look. So if these features are dunes, their slip face, which is the steepest part of the dune, should face the radar look. So should face the west in this case, meaning that the surface wind should blow from east to west. But if we take a look at the surface wind indicators nearby our study region, it is evident how the surface winds here flows from north to south, meaning that the slip face of these dunes should face the south, and so there should be no difference between left look and right look. For this reason, we exclude the dune hypothesis. So after this, we start to consider that the possibility that these structures could indeed be new lava flows. So as regards the geology, the situation is very straightforward because Siph-Mons, the first region of Siph-Mons is located on the western flank of a huge shield volcano in correspondence of a lava flow. So there is nothing much to say. As regards Niobe Planitia, also in this case, this region is located in composite shield-related volcanic material. And as I said before, some of these features seem to start from some shield volcanoes. Then we also analyzed the surface topography with two different products. The DAM digital elevation model obtained from the altimeter of the Magellan, and a second digital elevation model obtained by the stereogrammetry between the first and the third observational cycles. Well, in both areas with both these data, the feature that we observe stretches along the same path of the maximum slope. So also in this case, the topography is compatible with this hypothesis of lava flow. Then, to further constrain the nature of the feature we observed in Niobe Planitia, we made a comparison between some terrestrial lava flows. In the panel A and C, there are some flows in the Hawaii, and some of the features that we observed in Niobe Planitia. As you can see, in both cases, we can observe a fork in these features. In the Hawaiian case, it is clear that this is due to the presence of a surface obstacle, which is a small cone, is clearly visible, that deviates the path of this flow. And perhaps it is the same case in Niobe Planitia. Then, in this other case, we can observe a very linear feature. Here, the possibility is that the lava flows on a pre-fractured terrain, assuming this very linear pattern, as in this other example on the right, of a lava flow in the northern flank of Siph-Mons. Then, as a further analysis, we did the same change detection analysis on a terrestrial volcano in correspondence of a volcanic event. And we choose the volcanic event of the 2010 on the Pacaya volcano in Guatemala. So we choose an image before the event and an image after the event. And as you can see, in the image after the event is clearly visible this new white pattern structure, which is the flow, the new flow. And also our change detection analysis was capable to detect this new flow. And as you can see in the backscatter cross-section, also in this case is clearly visible this difference between the two different images, and the amount of difference is in the same order of magnitude that we measured on Venus. So, concluding, we observed significant changes in the backscatter in two different regions on Venus in correspondence of lava flows. And according to our analysis, these changes are mostly likely due to new lava flows and so ongoing volcanic activity during the period of the Magellan mission. That's my last slide with some references, and thank you for your attention.